The Insider's Guide to Energy podcast is proud to announce the Data Science mini-series in collaboration with Forbes, problem-focused and solution-driven. On this show, we will be covering everything from data science fundamentals to trading, forecasting, working with large datasets, and even skills required. Make sure to follow us on Spotify or Apple Podcasts so you don't miss out on new episodes.
Welcome to Insider's Guide to Energy Data Science mini-series. I'm your host, Chris Sass, and with me is my co-host, Selina. Selina, how are you doing today?
Good. Hi. Thank you. How are you?
I am great. I am really excited about the episode we're going to make today. So much about renewables and where we're going is about predictability and understanding weather and other elements. And the data science that makes this possible, I think, is going to be a really interesting episode. What are you looking forward about today's episode?
Well, yeah, we're talking about renewables and how we always need more of them, and about how, the entire system is starting to be dependent on renewables, which are kind of not that easy to predict. And I'm very excited today to hear from our guest about how we can do better and how the technology is helping us here and maybe what comes into the future.
All right. Well, rather than us pontificating, why don't we bring our guest on board and hear what they're doing in this space? So I'd like to introduce Dr. Martin Fengler. Welcome to the program.
Thank you very much. Hi, Chris, and hi, Selina. Nice to meet you.
So Martin, I have a good idea of your background because we did the pre-show with you and we invited you to be a guest, but I promise you our audience doesn't exactly know who you are or what company you're with yet. So let's start with who you are professionally and what you do.
Yeah, so I'm a mathematician by training. I did my PhD in a very theoretical part of numerical weather prediction, now about maybe 17 years ago. And I started working with a private med company for about 4 or 5 years and then founded Meteomatics in 2011. So we are almost 11 years old.
So weather has always been one of your main interests, I would say, and that led to the founding of your company.
Well, after I worked for a private med company, I, of course, had already some sort of specialization in that field. But I did my private pilot license, which let me end up at the airstrip several times waiting for the fog to raise. And this was actually one of the moments where I was confronted myself with bad weather forecasts. As a mathematician, you're typically more interested in minimizing certain error measures like a mean absolute error or an RMSE and stuff like that. But when you are confronted yourself with bad weather forecasts, and this makes you think. And
in real life, so to speak.
Yeah, exactly. This was a reason why we decided here to pick up on this challenge and trying to do something new, something better.
So weather forecasting has been around for as long as there's been weather, I think. People have been trying to guess weather. And as we were setting up the show, we were joking about crystal balls and how one might do it in the past. Where are we in the evolution of the science, and is it a science of weather forecasting?
Yeah, I totally agree. A lot of people might argue that we are throwing dice all day long. No, it's this is not really the case. There's a lot of science going on, and I think there's no other area where you really require such a supercomputing capacity as we do in weather. So technically, we are solving partial differential equations. It's the Navier-Stokes equations coupled into thermodynamic equations. And we need to know an initial state. And then, of course, we have the law of physics and the numerics that takes us forward. But the main challenge with modern weather forecasts is not necessarily the compute power, but that we have actually no idea how the weather is right now. I know this is super irritating for most of our people here in this audience, but it's actually something different of just looking out of the window and spotting a cloud or a sun, and to tell this supercomputer where it is right now and what does it mean in a physical sense and where the cloud is going to move. to move to. And this is a key challenge in weather forecast, to get the initial state right and get all the different weather data from stations, radar, satellite channels, and so forth into one place, and then to apply the numerics.
I think we're already right in the middle of things, and like we were already touching on the key question that we would like to tackle today. So, I mean, it's a data science podcast, and I'm very curious to talk more about the data because, as you said, thing is first just setting the stage or just saying what is the weather right now. So, what kind of data goes into this, into answering this question, and what do you do, like especially as Meteomatics, to answer this question and then take it from there?
So first of all, there's already a lot of data freely available, typically from national Met services, classical weather station networks, for instance. But they give you only some limited information about the weather that is going on, because when the rain hits the ground, the weather has already happened. So you have the 2 meters temperature and the wind speed, but to get into the what we call the weather kitchen, we need to look into the higher altitudes of 8 kilometers aloft. So we need really data from the higher levels, and this is helping us to in the forecast, and there we of course need radar data, satellite information, remote sensing data like LiDAR systems and microwave radiometers. So there's a bunch of different instruments available. All of them have their advantages and disadvantages depending on the situation. But this is some just giving you some limited idea about the current conditions, and anything that you could contribute by proprietary data sources or third-party sources that are initially not designed to deliver weather information, such as aircrafts or even cars, for instance. They help you to improve this initial state. And we at Meteomatics, we have developed over the last 10 years also a drone technology, which we call the Meteo drones, essentially drones that are equipped with weather instruments, helping us to get weather readings from the upper air. And these drones, of course, are super advanced. So it's not just having a DJI equipped with a thermometer, but our drones need to cope with high wind speeds of 100, 120 kmh. They need to be able to fly out to 6 kilometers, fly under icing conditions, and so forth. So these are really advanced systems, and they add something here to this overall jigsaw.
Just practical question, where do those drones fly? Like, what is your geographical space of your business?
So for the time being, if it comes to the drones, we are operationally operating them in Switzerland, but of course we are selling them also to other countries, and some of our customers from the US, for instance, are operating them in the US or in Japan or in other European countries. We distinguish here between mobile systems that are more meant to support field campaigns and those stationary systems where you should think of a drone in a box solution. So you do not need an operator next to it, but you can completely remotely operate such a drone system.
All right, so you've got drones. You mentioned a plethora of sources. There's just all kinds of different sources. So let's look at this as a data problem. So you're getting data from all these different sources. So how do you kind of rationalize that data to be usable? And then how do you get it? Like, what kind of time frames do you need this data? How rapidly do I need a piece of data, and how real time does it need to be? Or is my car, when it gets back to my house and gets on the Wi-Fi, going to feed some data that helps you later, or that plane when it lands, or am I getting telemetry and getting that in real time? So a couple questions, right?
Yeah, and actually really tricky ones. There are two two main challenges. One is to get the different data in-house in a timely manner. And of course, if it comes to weather stations, for instance, you like to have real-time data. So maybe with little delay, 1 or 2 minutes delay, something that you would expect, and that you would have updates every 5 to 10 minutes. And the same maybe also with radar data. And nowadays, it's also the case for satellite data that you are able to get rapid scans every 5 minutes from space. And this, of course, gives you already a huge amount of data, non-structured data typically. Every data source has its own format. And if you think of Europe, every single country does its own format for everything. And then typically down just to the country border. And then you need to create composites of radar images from the different countries. And once you have done all this homework, then you can start thinking about running a model. But of course, no one needs an old data and also an outdated forecast. So again, all of this needs to be parallelized, and then you create your model forecast. And then the second challenge comes up, and this is actually one that is typically forgotten if you look at, say, work from National Met Services, but also at other private meteorological services, namely the delivery piece of work. Just to give you an idea, the model output from our pan-European 1 kilometer model, for instance, creates 200 terabytes of output per day. And we need to have an engine in place that allows slicing and dicing in real time, because people are not really interested in getting a huge binary flat file and shipped into an FTP account that might be 200 gigabytes in size, if they're just interested in a certain slice maybe. But they are just interested in a specific location and like to get the wind speed at 120 meters height above ground level. And this is a complete different challenge. And we have built a proprietary technology which helps us to take in this output and do the slicing and dicing in real time, and to deliver time series to support machine learning applications. Same, by the way, is also true for historical data. As you can imagine, we built underneath a platform which provides currently real-time access to around 20 petabytes of data. And this is a huge challenge, of course, from a technical perspective. But once you have it, it's also enabling many super interesting applications across data science.
Let's dive into this right now, because I'm just kind of swirling my head about those huge amounts of data. And I understood that you introduced a technology, or you developed a technology to deal with all these kind of different data, different formats. I was also shaking my head when you said it's all national things. So when you go beyond the border, you have different formats and different stuff to deal with. And when it comes to hardware, you already touched upon the topic of a supercomputer. So that's something that is also in your company. And maybe you can just talk a bit more in detail about this technology as far as you can, that makes this possible to cater so specifically to your clients, and they have maybe just very particular interest in one location.
So in terms of technology, the supercomputer, for instance, is actually a sort of a classical AMD cluster as of today, as you have it, for instance, also in Microsoft Azure. This is something that is available even for smaller companies like ours. I mean, we have around 75 colleagues only, but we can already afford this compute power, and this is good news. And the cluster we are talking about has a size of around 40,000 CPU cores, and this is the one challenge here. Of course, we talk about the HPC context about Linux nodes, and then talk about Fortran 90 codes that are running on these systems. And then once we have this output, we take them to high memory nodes. And there again, we have a Linux backend and combination of C++ and other programming languages, which allow us to handle this huge amount of data. And this is maybe from a technology perspective what we are doing there. And of course, software-wise, it's really that we had to go the rocky, hard road to build this on our own. We've really built a proprietary technology here, mainly because ordinary database technologies are just not fast enough, efficient enough to deal with this special nature of data.
So you've built a proprietary system. Your software. You put it on a cloud instance of a supercomputer, for what I'm hearing, so you can scale it up and down where you need to. I guess where you talked about building this proprietary because it didn't exist. So how does this differentiate from other models of production? Or why do I need, or how do you not? I guess, what's the magic of bringing so many sources together and getting something meaningful, different result than me just going to like a local database of weather forecasting information that's out there and doing this, right? So you add a bunch of layers of sensor and capabilities. So you have more signal to work from. I guess the question is what makes this different, right?
Let's leave the supercomputer aside for the time being, because this is mainly used to solve the numerically the partial differential equations of the computational fluid dynamic problem underneath. But let's focus on what we do in terms of refinement of even already freely available data or commercially available data that are more coarse grid typically. And that is that we blend them among other data sources like radar and satellite data, but in particular also with high resolution digital elevation model data. So even in areas where we don't run a proprietary weather model, we can still enhance the existing output of some global models by combining this with high resolution digital elevation model in 90 meters resolution, which helps us to resolve fine granular details like valleys, mountain ridges, and this adds tremendous value here. And I think this is.
Maybe I can just come in here because I was just so interested about what you just talked about, the granularity of the data. And because I think everybody knows that you live on one side of the city and you talk with somebody on the phone, they say, oh, well, it's raining here. And you say, no rain, not at all. It's sunny here. So it's just, I don't know, just a subway ride away maybe, and the weather can be totally different. And especially when it comes to renewables, what we should also talk about is you have totally different wind conditions on one wind park, and then maybe the other one is just on a hilltop, or there's something between, or there's a forest, and it changes the conditions totally. So I understood that the model that you provide is very granular, and that's something that's very special about that. Is that right?
Yeah, so just to give you an idea, if it comes to these weather models, we should distinguish between global models and local area models. So global models come at a resolution of 8 to 10 kilometers. And this is super coarse. I mean, think of the Swiss Alps, and the Swiss Alps are maybe just 200 grid points. That's it.
Okay.
And of course, you need to improve such a coarse grid model, and then you could apply fancy machine learning and deep learning techniques. But here physics wins. So you need to increase the resolution and apply law of physics and actually solve the computation fluid dynamic challenge. And this comes at a price. So once you increase the resolution by a factor of 2, you need to invest a factor of 10 into the computational capacity. And now we are running a 1 kilometer model across Europe. And maybe the German Met Service, for instance, is also running a pan-European model in 4 kilometer resolution. And so the resolution is already 16 times higher horizontally. And then, of course, in the vertical, you need also to add more layers. And if you ask, so what is different about your data and data source than others, then is one is the resolution and accessibility, but also that we ingest into our platform also the upper air level information, which enables us to come up with the wind at hub height in 120 meters height, for instance, but also at 5 kilometers height if you do business with the aviation industry. And Airbus, for instance, is a customer of ours, and there we support their high-flying Zephyr drones that operated at an altitude of 15 kilometers or 20 kilometers height. And only when you ingest all of these data, and this is a 3-dimensional data set apparently, but also time dependent, so effectively a 4-dimensional data set, and once you can handle that, then you can also work in these exciting projects. But something that you typically see is that Met Service are just focusing on the 2 meters temperature and add maybe a weather symbol like you have it in ordinary weather apps, and that's it. But weather is much more. It's really a 3-dimensional data set, and effectively a 4-dimensional one if you consider also the time dependency. And this is something that gets completely forgotten, generally speaking.
Mm-hmm, mm-hmm. So we dived in a lot into the data now, and we learned that physics always wins. For example, that's a key takeaway. And I would like to go a bit on the business side and learn more about the concrete offerings that you have for your clients, because this high resolution model for Europe is something that's very very particular about Meteomatics. But how do you make this work for your clients, or how can your clients get the most of your that what you can offer?
So
especially in the energy industry, or when we talk about renewables, of course.
So what we effectively did is that we built this proprietary in-memory database technology in which we ingest all the different weather models from the different national Met services, radar data, satellite data, and so forth. And in front of it, we have what we call the Weather API, a really simple interface, easy to integrate with, and there are many open source connectors, for instance, to make it super convenient. For instance, data scientists are typically using Python or MATLAB and R. This is what we see quite often. Then they can directly access these data just with a few lines of code and start working with it. And from a business perspective, well, it's a SaaS model. So the customers sign up on a monthly subscription, and then they get charged in terms of volume, whether they need historical data or even gridded or graphical data. And this is the business model behind.
So how are they then taking that API and then connecting it? Let's say you're balancing a grid. Let's say that was my mission. So what kind of applications are they taking your information in, and what kind of models are they then using your data for to make their business plans?
To balance a grid, there's, of course, different applications. Nowadays, if it's about renewable energies, they like to forecast certain assets within their area of responsibility. So there are solar, wind power turbines, solar power plants, and then you take from our API either already a power forecast, or if you'd like to do the modeling yourself, then you retrieve the global radiation, diffuse and direct radiation, maybe also snow depth, because snow affects during the next couple of months quite heavily also the solar power output, and the same for the wind forecast. And then, of course, you can come up with a power forecast for those assets in your transmission area. Then you have, of course, the demand side. And this is typically depending on the outside temperature, but also on the radiation and some other factors. And this helps you to get an idea about the demand. So you have the production side and the demand side. Of course, the demand side depends not only on weather, but also you have calendaric effects, and you have also weekdays or holidays, seasonal effects that play an important role if it comes to demand forecasting. And then you can look at the balance of it. And then you have also really technical aspects in operating such a transmission system. For instance, do the power lines allow you to transport the energy? Because they might be affected by high currents, expand, and there might be some certain limitations if it's too warm outside, or if it's not windy enough to do some cooling of the power lines. So there's also a technical angle to this challenge. And then, of course, ultimately, you have trading companies who might be interested in exploiting this sort of bad planning, or might exploit the difference in production to actual readings and to trade on it and get some advantage out of it.
For sure. From my experience, when we work with clients and in big data science project, in the beginning, there's always the wish to do everything themselves. So get the hand on the raw data and then do the forecasting themselves. Sometimes this changes over the course of a project because, one learns that there are companies that do nothing else all day than just to do this very specific type of modeling or forecasting. And so I was wondering, what is your experience with your clients? Just roughly, maybe would be interesting about doing it themselves, or as I just understood from you that you also provide forecasting and not just the model, the weather model.
Yeah, you're absolutely right. This is something that we see quite often. And to that extent, the Weather API supports also this approach. So you should think of a super horizontal product. I mean, we can sell it to the energy space, but also to the automotive space, logistics, aviation, even government entities are utilizing these data for some of their applications. But at some point, people who run a specific portfolio, and they have a wind turbine in a specific location, and they know exactly the turbine type, and they have some sort of power curve and other parameters like the rotor diameter and so forth. They like to get a super accurate forecast for this. And of course, initially they try to do this on their own, but in case of wind and solar power forecast, we might also support them by delivering them already a calibrated forecast. And then we are immediately in the field of classical machine learning applications. So we have the historical readings from the client in terms of kilowatts
produced
power or energy. And then on our end, we have the weather information. And then, of course, we map this. And you could think of a machine learning model in between to come up with a calibrated, super accurate forecast for it. But this is something that is only then relevant for this single customer. It's a really bespoke solution, whereas the weather API is super horizontal. To that extent, we are in the first step always some sort of enabler, but also happy to do the last mile solution for some of the customers in the renewable space. And this is why we have, as of today, around 150 customers from the renewable energy industry.
So in order to produce all these kind of sounding magical things, although you talked about some of the hard work, how many different models and how complex is this to do this? I mean, just curious. It sounds like to deliver what you're talking about to all these different stakeholders, that you're managing all kinds of models and a lot of compute on your end.
Yeah, so the trick really is to harmonize the different data sources. So if you ingest maybe the data from the US American Met Service or the European Met Service, UK Met Office, Meteo France, DWD, then they all come in different resolutions and data formats, and even variable names change. It's really a disaster, a complete nightmare to deal with these data. But once you have ingested this into this Meteo cache and the weather API, you have a super clean interface. And as an analyst, for instance, developing Python code, then you can just change from one model to the other by changing the model source. So you change it from NCEP GFS to, say, UK Met Office UM10 or the ECMWF IFS model without changing anything else.
Because everything looks the same.
Exactly. So from a development perspective, all the pain has been shadowed by this API. And this is where our technology adds tremendous value. So instead of reinventing the wheel in any of these trading companies, among all of these analysts, they start from day one with working on their actual problem and not trying to figure out how to transfer data to an FTP server and to install some monitoring in case that something is delayed and stuff like that. So this is all done in our service layer, so to say.
So you're a clean data source for them to make quick business choices with and use. So how do you scorecard? Do you go back historically and judge how you did on your predictions? How do you know that the information you gave me for the last 6 months was accurate?
So we operationally we monitor the performance of our forecasts on certain wind parks, solar farms, but also on weather stations. So it's something that we do internally, and we can look into the skill of different models, which it allows us also to do some sort of back testing. But the energy landscape is super competitive. So when you come up with wind or solar power forecast, you're not the only one in the market. And what you typically see is that larger trading companies and utilities are doing benchmarks all the time. So when you decide, okay, I'm ready to take part in such a competition, then you should approach these players, and then you ship these data 2 to 3 months, most likely for free, to them. They test it and compare it with their existing forecast. And if you have a good solution, then they might negotiate on a contract with you. And this is what we see quite often. And typically you have 10 to 15 participants in such a benchmark. And of course, you need to be among the first 3 to be really relevant. And when you're among of these first 3, then you get a contract. It's as simple as that. So we have this sort of third-party calibration points, reference points that the data we deliver are of good quality, I think.
Well, in the very beginning, we were talking about how to measure maybe predictions, or how to minimize errors. But more broadly speaking, what is the goal when it comes to forecasting, or where is the industry right now? Because of course everybody wants to have accurate weather forecasts, but what does that mean? I mean, for tomorrow, okay, probably it's pretty good. For the day after tomorrow, okay, but are we looking at getting more accurate forecasts for the next I don't know, 7 to 20 days, or is there, I would say, like a cutoff or a trade-off in the cost benefit consideration, that you say, well, we're just trying to maximize our power in forecasting until this time horizon, and everything after that is just not worth it? Or does it even work that way? You can just throw more data or more money at it and you get better forecasts out? Or how does that work?
Yeah, so maybe it's time here for some sort of expectation management. We are especially committed to get the intraday right.
Okay.
So even if, of course, there are products around that go out to 3 or 4 or 5, 6 weeks, maybe 2 years in advance. It's always about managing expectations around that. If you ask me, Martin, do you have a product that tells me during summer at 9 a.m. in the morning where the storms are going to be located in the afternoon? And I must admit, no, we don't have such a product yet. Nevertheless, we are getting closer to it. And this is a combination of compute power and adding more and more data sources. And drones, for instance, might play a role, but of course are not saving the entire planet here. It's about getting all the different data sources into one place and to get this fixed. And if it's about 5 or 7 or 10 days forecast, well, then it's about the measure you add here. You might have good idea about the temperatures, for instance. Precipitation is already a bit more tricky. That is maybe giving you some trend. And the trick that meteorologists do is that they try to identify how stable the current weather conditions are, and adds a little bit of noise to the initial conditions, and then do a rerun. And they then do another run with different noise level, for instance. And this is giving you then a new variant of a forecast, and we call this ensembles. And these sort of ensemble forecasts give you an idea about the uncertainty in the weather forecast. And for the first time, you can actually start hedging your trading position against the uncertainty of the forecast. So you're already aware that we don't know the temperatures, the exact temperatures on the next weekend, but you have some quantiles, some probability,
like a corridor.
density, a corridor in which you could expect to land.
Mm-hmm.
And this is giving you a huge advantage, especially if you start connecting this uncertainty with a cost functional because of the particular trading position that you're doing. One of our customers, for instance, an airport operator, has the $1 million button. What does it mean? So if he hits this button, he needs to bring in people to clear up the runway because of fresh snow. And this costs him literally $1 million. Each time he hits this button, he has 500 additional people on the ground with machinery to do the runway cleaning. So why does he hit the button? I mean, if he doesn't, he could save $1 million, right? But if he doesn't hit the button and there is snow coming, it costs him $5 million. that day. And once you have this sort of cost function, or this is how we call it as mathematicians, you can start optimizing your strategy when you should hit the button or not hit the button.
Knowing about the levels of uncertainty that you're looking at.
Exactly, because you can map the uncertainty into real money. And this is super useful and helps you also to do trading over maybe 2 to 3, 4 weeks, something like this in advance. Nevertheless, the models that are used for these long-term forecasts are super coarse. So we talk here about models that have 10, 15, 20 kilometers resolution for the next couple of weeks. If it's about an outlook, a seasonal outlook, it's maybe 100 kilometers. If it's a climate outlook, maybe 200 kilometers resolution. And then the Swiss Alps, for instance, are just 3 grid points. And you need to be aware of these things before you start looking into very local effects that you might see because of artificial downscaling artifacts, things like that. That the underlying source is already a bit shaky on these longer.
But in the trading example, are you working with algo traders? Is that?
Yeah.
And if you are you responding in microseconds, milliseconds? I mean, you said there's 2-minute delay here in the system and a little bit of pieces. And so in trading, that's forever if it's an algo trader, right?
Yeah. So within energy, to my knowledge, you don't have at the moment these sort of high frequency trading as you have it in the ordinary stock exchange, where people are looking at the Bloomberg ticker data and within milliseconds they try to do a trade. That's mainly because to get access to the exchange, for instance, in Leipzig, the power exchange is limited to only certain user groups, and there are maybe a few hundreds that are taking part in this. And then it's a matter of volume, trade volume, and also the slicing. So energy might be traded just in 15-minute intervals, for instance. That relaxes this situation. So it's still sort of real time that you need to answer these sort of queries, for instance, but it's not that high frequency. It's this high frequency as you have it.
Yeah, it's in minutes, right? So with distributed energy, that gets more. The second part of that, then, if it goes to traders, so if it's not that tight, is what percentage are you right? So you can't be 100% right in your forecast, clearly, based on what we're saying. And you're saying, hey, I can't even tell you if it's going to rain this afternoon at 4:00 for sure. So you're making some calculated guess that they're going to kind of arbitrage on, or they're going to bet on you're statistically winning, right? So how often are you right?
So I think it's best to answer this not on a yes or no, how often are you right, but if you look into forecast errors. And for instance, in Germany, you have an installed capacity of around 40 gigawatts in wind power and around 40 gigawatts in solar power. So the total installed capacity is around 80 gigawatts. And when you look into the German total power production, you see typically an intraday error that might be in the magnitude of 1 gigawatt, maybe. And then if you look into a forecast, then it could easily already be on day ahead, somewhere in the magnitude of 2 to 3 gigawatts if you look into the bandwidth of the different forecasts. So it's really a plume of different possibilities. And the challenge here is, of course, that subtle differences, small errors in the wind speed, go into the power production with a power of 3. So this is by, again, the law of physics, how the power law works here when you convert from wind speed to power. And this is enhancing all the small differences. And on a total portfolio for Germany, it's somewhere around 1%, maybe less, in terms of an RMSE. And if you go to a single turbine, for instance, it might be in the magnitude of 10 to 15%.
Well, after we talked so much about the current status of technology and what Meteomatics can do, I'm wondering where are we going from here? So what is going to happen in the future from a technology standpoint, but also from a business standpoint, expecting that the forecasts will keep getting better and getting more accurate. What is gonna happen in the next few years? Maybe if you could give us a lookout.
Yeah, we have just started running this pan-European high-resolution weather model Euro 1K. And it's quite obvious once you have done this and delivered this to take this to other territories. And we are just about to make the step across the pond, setting up an US entity, trying to get our feet on the ground, and actually looking for some CEO right now. So in case that some of you are interested in, just shoot me an email. But yeah, the next logical step is to run such a European-like model also for the US. And of course, the moonshot vision is to do this for the entire globe one day.
Well, awesome. We were pressing up against time. I've enjoyed this conversation immensely. I think I have a better understanding of what you do, and the amount of data you're working with is impressive. The number of sources that you're bringing in and making it meaningful that somebody can just take a Python script and drop your data in and just use it. That's pretty powerful to me, and I think it's enabling. My final question is: I'm a big sailor. Do any of the Sail GP teams use your data for sailboat racing right now? And if so, what country?
So none of the big ones, but we support some companies providing apps for this sort of community. There's, for instance, Savvy Navy is one of our customers, and there are a few more, but Savvy Navy is definitely pioneering here this field for us.
Oh, awesome. Yeah, just curious, not really related to the mainstream, but it was just a curious thought I had. I want to thank you so much for being our guest on the show today, Martin. It's been a pleasure.
Thank you, Christian, Selina. Thank you. Take care.
For our audience, we hope you've enjoyed this content as much as we've had in making it. If you have, please share this with your friends. Don't forget to like, add comments, subscribe, and follow us. And we look forward to speaking to you again in another episode of the Data Science mini-series that we're producing. Talk to you soon. Bye-bye.